Hi there, we're Group 3, and this is our interim presentation and analysis and redesign of a blender. So about blenders, by foods or other substances. They usually have a plastic base and electric motor covered by a plastic housing. Blenders can function at various speeds to provide a necessary cutting force, and they have a metal blade which sits at the bottom, and the pitcher is covered with a plastic lid. So about our target customers and production volume. Our primary customers are home cooks who need to blend ingredients used for meals, and our secondary customers are workers in cafes or restaurants who use blenders to make drinks and food. The annual demand for blenders in the US is 25.8 million, and the estimated annual production volume is 1 million units. This is our fast diagram. On the left here, you can see mixed contents, which is our task function. And to the right, you see that it branches off into multiple functions. The ones in black are the primary, and the ones in red are a little more optional. The create force can then branch out into things like chop contents and handle various size contents. And enhanced product has only one branch, which is customized speeds.
To assemble the blender, we developed two assembly sequences. In this first assembly sequence, it includes a large blade subassembly that is attached to the main assembly as one part. And this assembly sequence builds around the lower housing cover and then adds on components in multiple subassemblies like the housing mainframe, electronics, housing outer cover, and jar. For assembly 2, it is much more linear, and the main difference is that the blade parts are all added separately. But the smaller subassemblies, the housing mainframe, jar, and housing outer cover remain the same. Comparing the two assemblies, we can see that assembly 1 had fewer but larger subassemblies, while assembly 2 had many smaller subassemblies. After comparing the two sequences, we found that assembly 2 is more efficient of the two sequences, and based on our scores, we can see that this is due to the ease of locating parts, transferring the assembly, and fastening it.
Here we have our function component mapping matrix, where we map the components of the blender assembly to the leaves of the fast diagram. The leaves are the basic functions performed by each of the components. The most important components are those that perform the most functions, which include the pitcher and the blade screw. The most commonly performed function is protection of internal mechanisms, and that's performed by 7 of the components listed. With more components performing the same role, we have the opportunity to reduce part numbers. Here we have our bill of materials. To create this, we used a production volume of 1 million blenders. We have the name of each part and then the material it's made from. As you can see, most of our parts are made from plastics made from injection molding. Then we estimated the material cost using hubs.com and custompart.net. To estimate the assembly time, we used the manual handling time and manual insertion time charts provided in the lecture, and used that time and an average US wage of $20 per hour to estimate the assembly cost. From there, we were able to calculate the total cost of the blender to be $30.81. Next, we have our quad chart. This, we grouped our parts into functional importance and manufacturing costs. This helped us determine which parts needed the most improvement and which parts we could preserve due to their already beneficial qualities.
To begin the family design process, we started with the functional development table. In this table, we have 2 columns differentiating the functions based on whether they are similar or different for the 2 customer groups. Based on this table, we found that the only function that's different between customer groups is blend various sized contents. Using the function component mapping matrix, we connected this functional differentiation to components. This information is presented in the component commonality table, where the modules are the components that meet the blend various size contents function. The common module for both variants will be the base of the blender, including its internal motor, buttons, and blade joints. The module will be the blade assembly, which consists of a blade, blade screw, and blade sleeve. For the secondary module, the blade assembly is modified to be a longer shaft with multiple blades, and this will help blend larger food sizes and quantities found in restaurants. For the original product family assembly sequence, we have two separate lines representing two blender variants. In order to merge the two sequences for the product family, we can start by modifying the order and start with the housing lower cover, adding all the internal lower components until we reach the upper blade joint. From here, the first variant will branch by placing the blade, fastening the blade screw, and finishing the assembly as shown. The second variant will instead require we add the sleeve, 3 blades, and blade screw, then finish the assembly sequence as shown.